Good evening, ladies and gentlemen. Very warm welcome to Gresham College. My name is Barbara Anderson, and it's a great privilege to have Stuart Clark with us. I think he needs little introduction to most of us. He's a very well-known writer. This is our second lecture this academic year, my first because I was on holiday. It's a rather special occasion. In addition to the lecture, there is going to be a reception afterwards, and at that reception you will have the opportunity to buy one of Stuart Clark's books at a special knockdown price for one night only of £13. But do join us for a glass of wine regardless. The wine will be served in the adjacent room, and then you can take it out into the courtyard, and the books will be signed in that corner there. To those of you who've come here for the first time, please don't leave without our programme of events for the coming year, because we've got lots of exciting things coming up. Ian Morrison is our new Professor of Astronomy, and his first lecture will be on the 26th of October at 1 o'clock at Staple Inn Hall, which is just down the road a little way by the tube station, behind the black and white building. And then, as it's his inaugural lecture, there will be a reception after that back here. But now it's a great pleasure to hand over to Dr. Stuart Clark.
Well, thank you. It's a genuine pleasure, if not a thrill, to be lecturing in Gresham College. That's an academic thrill, of course. The birthplace of academic astronomy in the UK. And let me also add my endorsement of Ian Morrison, who is a superb lecturer, and I'm sure that he will teach you many things over the coming series of lectures here. So I'm going to talk to you tonight about the Sun Kings. Being in a historic place, I thought we'd look at some history. And over the course of the next 3/4 of an hour or so, I'm going to sweep you back into the 19th century and look at the way in which the astronomers of those times replaced every bit of myth and speculation about the way the sun works and how it affects the Earth, and put in place the foundation stones of our modern knowledge about the sun. Before I take you all the way back there, though, let's step back just to Halloween 2003. This is the SOHO satellite, and it's an electronic watchdog that sits between the Earth and the sun and constantly monitors the sun. The sun is this ever-changing place. It's the powerhouse of the solar system, and it's a huge nuclear furnace that generates all the energy that then radiates into the solar system and keeps the Earth and all the life on it going. It's an extremely changeable place, and SOHO is there to watch for these changes. It changes on a daily basis in a number of ways. The most obvious way in which the sun changes is that periodically dark blemishes appear on its surface, and these are called the sunspots. We now know that the sunspots are caused by magnetic fields that well up inside of the sun, and they burst through the surface, and they look rather like, if you could see them, they'd look rather like the pulled thread on a woolen jumper. And as these great structures rise into the solar atmosphere, so you see these dark features, the sunspots on the surface. The sunspots are the site of solar activity. And at Halloween 2003, for about a fortnight period, the sun went through one of the most active periods we've ever known it to go through. In the course of that fortnight, something like 17 solar flares exploded. Now, the solar flares are the energy that gets released when these huge tottering loops of magnetism collapse into smaller structures and more stable structures. These are the two giant sunspots that appeared on the sun at that time, and these are the ones that gave rise to these solar flares. Every time one of these flares explodes, it releases colossal quantities of energy, over 1 billion times the energy of the Hiroshima bomb in each explosion. They're cataclysmic events, and because of the way that SOHO works, we actually have a movie here showing the sun during that period in which you can see the flares. Now, this movie covers a period of about a fortnight. It's taken at ultraviolet wavelengths, and in this time, instead of seeing the sunspots as dark, you're seeing the hot gas in the magnetic loops above the sunspots, and that's appearing as bright. Now, the first sunspot group is sort of closing in towards the right-hand edge of the picture. The second giant group is just coming around on the limb on the left-hand side. Every time you see these little flashes, those are small flares going off. And as you start seeing, there starts to become some really enormous flares, and that seems to cover the screen in static. And what is happening there, there's a big flare just gone off from there. You see little bits of static coming up here. This is one now on the left-hand edge. This is the other enormous sunspot group. Big flare there, and suddenly this whole sort of static overcomes SOHO. All of these, another one there, all of these events contribute what we call space weather. And not only is this releasing energy in the form of X-rays and gamma rays, but it can also cause giant eruptions. The sun is surrounded by this enormous atmosphere of gas, and when these explosions take place, that can actually launch huge clouds of this gas into space. 1 billion tons of solar material can be thrown off. Each one of these flares then can trigger these enormous eruptions of this solar material. And if we sort of move out, SOHO has a number of different cameras from which it can watch the sun. And here they're all layered together. And you can see the green image of the sun in the center. That's the one we've just been looking at in close-up. And the other wider angle images show the actual eruption of gas into space. This time it's date stamped as well, and you can see we start on October the 25th here. So as we move around, you see little puffs and explosions there. October the 28th was when the first of the massive flares and eruptions struck. There it goes on there. That's a head-on collision between this 1 billion tons of million-degree gas and the spacecraft SOHO, and then of course it swept on and hit the Earth afterwards. There were other eruptions throughout this week. You always know when you're getting a big one by the amount of static that you get. Now on November the 4th, look over towards the right-hand edge and you'll see a very big eruption. There it goes there. Now that one was actually directed away from the Earth, which was just lucky because that was the biggest of these Halloween eruptions. Now I mentioned that they were hitting the Earth all the time, so as you might expect there was some effects from all of this. The first of which was that these huge clouds of electrified particles can charge up spacecraft, and as the charges build up on the spacecraft, so they can short circuit, and that can damage the electronics. And in fact, the Japanese lost the Midori 2 weather satellite. It went silent during the storm on the 28th of October and hasn't been heard from since. Half of NASA's spacecraft reported malfunctions in some way. They weren't fatal, and what most of them were is that the satellites of today hold themselves upright in space, and they hold themselves upright and in a fixed orientation by having little telescopes on them called star trackers. And these star trackers watch the night sky, and they monitor the positions of the stars, and if they notice any slight movement in the stars, then they fire little thrusters to keep the satellite stable. When the satellites are surrounded by these great big clouds of electrified gas, however, it blinds the star trackers and they lose sight. Now, the spacecraft will try to correct for that. It thinks, oh goodness, where's the stars gone? I need to try this, I need to try that. And it will just dangerously fire all these thrusters. So what spacecraft do is just recognize that something's gone wrong like that and shut themselves down. And then they wait for ground controllers to send up resuscitating signals saying that the danger's over, turn on, see if you've if you're okay, or if there really is anything wrong with you. Now, perhaps the best example of just how powerful these storms were is that NASA also had the Mars Odyssey spacecraft out in orbit around Mars, and it carried with it a radiation monitor. The radiation monitor was designed in order to measure the amount of exactly this kind of solar radiation that would reach Mars, because Mars has a very thin atmosphere, it has no ozone layer, and it is in fact one of the biggest problems if you're going to send astronauts to Mars, that you don't have this big bountiful atmosphere like the Earth has protecting you from the radiation. Well, the Mars Odyssey radiation monitor was burnt out by the Halloween storms. NASA had completely miscalculated just how much radiation it was possible to receive at Mars. On the Earth, there was all sorts of communications blackouts. All of the expeditions on Mount Everest, they were lost contact with. There were forest fires in California at the time, and the radios wouldn't work properly, so they couldn't correctly coordinate their efforts to fight these fires. The marine disaster network, the emergency network there, was blacked out as well. So, and then there were other somewhat more trivial communications issues such as mobile phones and satellite television being blacked out for people. Perhaps most seriously of all, this was the first time that passenger aircraft were diverted because of the risk of high altitude radiation. The solar flares on the 28th of October and again 2 days later on the 30th were so large that the FAA decided that they would move all aircraft away from the polar regions. These have been becoming increasingly popular as routes to go over the poles of the planet. The trouble is, that's where the magnetic field of the Earth funnels all this solar radiation down into the Earth's atmosphere. And so when these storms hit, as a precaution really, nothing else, they diverted the planes down to below latitude 54 and brought them down lower into the atmosphere so that there was more air above them to provide some protection. But a question that occurs in my mind for all of this is, did we have a really quite a lucky escape? All those things that I've mentioned to you, if the flare of November the 4th had hit the planet, could have been much worse. Perhaps it could have been GPS that was badly affected. Certainly, over that Halloween period, all the GPS signals became much more inaccurate than normal. And I think the clue as to what might have happened is that if we look back 150 years into the past to the time when we know that there was the biggest solar flare and subsequent magnetic storm in recorded history. So let me take you back then. We're in 1859, it's September, and we're aboard the clipper ship, the Southern Cross. And the Southern Cross is designed simply to go from East Coast America all the way down around South America and back up to Gold Rush, California. And it just simply shuttles backwards and forwards. On the night of September the 2nd, it was in temperate Pacific southern waters off the coast of Chile. And the crew were fighting a storm. They were fighting a gale that night. And as the water whipped against the side of the ship and the spray sort of fell away to leeward, the sailors would be turning their backs into the wind. And they began to notice that over towards the other side of the ship, the whole ocean appeared to be the colour of blood. They wrote in the ship's log, we were sailing in an ocean of blood. Now, as the storm started to abate a little, and they looked up, they saw, even through the covering of cloud that was left, that the whole heavens was glowing red as well. It was the most unearthly sight. The thought immediately struck them that these could be aurorae. These could be the southern lights. They were used to seeing them down near the Straits of Magellan, but never had they seen them this high up near the equator, and certainly never had they seen them encompassing the whole sky in this way. The next thing that they noticed is all the masts and the lanyards began to glow with electricity. Now this, they knew what this was as well. This was the St. Elmo's fire. And it was a sure sign that there was electricity in the air. And it usually was a sure sign that there was thunder and lightning storms around. However, despite the weather that night and the squalls, there'd been no electrical activity of that kind that they sailed through. Getting towards dawn, the clouds began to clear and they started to see through to the night sky. And here, not just was the sky still enwreathed in red, but vivid white bolts of light seemed to be flying upwards from the horizon to burst above them at the zenith. They wrote it was as if the very souls of all humanity were fleeing whatever cataclysm had engulfed the earth. A few weeks later, they arrived at San Francisco, or a little while later, they arrived at San Francisco, and they rushed to tell their story of this extraordinary night. And they discovered that they were by no means the only people that had seen these. In fact, around 2/3 of the whole earth was covered in this blood-red glow. The blood-red aurora of September 2nd, 1859 is the largest display, the most widespread of an auroral storm ever witnessed. It stretched down into the northern tropics. People gathered on the shores of the Caribbean islands, convinced that the neighboring islands were on fire. In the Midwest, in America, they thought that there were enormous prairie fires engulfing the states there. You could read by some of these lights. People were woken up by the brightness of the aurora and could read newspapers by it. This is an engraving taken from the time because it sort of loses something being in black and white. So I decided to put in a couple of sort of more modern images of the aurora to give a kind of feel of what it must have been like. So here's one here where you can see the redness. There's also some green in this image. It's very usual for the aurora to be green. It's very unusual for them to be totally red. And this is another sign of just how extraordinary the 1859 one was. But you can sort of get the impression that you could believe that this was a fire somewhere across the horizon. Now here's an auroral corona. If this were a moving picture, you would see these lights entangled, all entangled and moving. And this must be very similar to what the sailors on the Southern Cross saw that night. Another picture of the aurora, and this time I've popped in a picture of a telegraph office, because there was a sinister side to this great auroral display. It wasn't all just light shows. The aurora, the telegraph system, well, it was the internet of its day. It was the high-tech communication. Everything that you use the internet for today, so was the telegraph used by the Victorians. And as the aurora erupted into the sky that night, so the telegraph system around the world went down. It crashed spectacularly. Not only did it cease functioning, but enormous currents surged along the wires, setting fire to equipment in the telegraph offices, causing huge sparks to fly out of the equipment that was being used, stunning operators unconscious. Just as it was as amazing and as frightening, just as surely as if the internet were to go down today. And in this time period, what happened was that the politicians turned to the scientists and they said, what happened to our planet? And the scientists had to say, we have no clue. This is completely beyond our understanding. It is completely beyond our knowledge. There is something that has engulfed our world that we are helpless in its grip, and we simply don't know what it is. They did, however, have just a couple of clues. It was certainly known that the aurorae were linked with magnetic effects because Celsius, Professor Celsius, in the 1700s, he and a student called Huyter, they were investigating the aurora, and they had equipment out in front of them. And Huyter recalls later in his writings that as a great aurora burst over their head, he noticed that the compass needle was wildly oscillating around. Its lock on magnetic north was totally lost. And he said to Professor Celsius, look what's happening to the compass. Somehow these lights are magnetic. The professor, the wily old professor, turned around and said to Huyter, ah yes, I noticed that too, but I thought I wouldn't say anything just to see if you noticed it. Commenting on this comment, historian of astronomy Jack Meadows wrote in a footnote in one of his papers that says, I noticed that the relationship between professors and their students has not changed greatly down the ages. So somehow the aurora were magnetic. There was also one other clue, and that was what I've called here the solar lockstep. On the left is General Sabine. He was adventurer, scientist, and he tracked the compass readings across the globe in his quest for magnetic north. And he noticed that the compass needle points in a slightly different direction at the end of the day than it does at the beginning of the day. And he tracked this, and what happens is that get up in the morning, take your compass reading, and it points in a direction north. Over the course of the day, that direction that it points drifts very slightly, and then at night it sinks back again and starts its daily trek all over again the next morning. Sabine noticed that the amount of this deviation changed every year, and it went in an 11-year cycle. Sometimes it was very small, and it got year on year, it got larger and larger and larger until it reached a maximum, and then it shrank back to a small deviation again. By a most peculiar coincidence, the chap on the right, Heinrich Schwabe, is a chemist who decided he didn't like chemistry anymore, so he sold the family business and spent all his money on telescopes, and made an extraordinary discovery. The sunspots that I was talking about earlier are not constant in how they appear, in their position or their number on the solar surface. And Schwabe decided to keep a track of these fickle blemishes to see if he could build a catalogue of them. And he noticed that they began as being relatively few in number and only appearing at higher latitudes. as the years progressed, so the number of sunspots that appeared increased, and they moved down in latitude towards the equator. When Schwaber's solar cycle of sunspots was put, the graph was put underneath Sabine's graph of the magnetic deviation, they moved in lockstep with one another. When there were more sunspots, so the compass needle moved more every day. That was an extraordinary discovery. How could the sun, 93 million miles away, be responsible for compass readings on the Earth? The astronomer John Herschel wrote to the physicist Michael Faraday, and he said, talking of this, he said, "I think we stand on the verge of a vast cosmical discovery, the like of which hitherto has never been seen before." The reason he thought this is that since the late 1600s, when Newton had developed his law of universal gravitation, the philosophers and the scientists of the time believed that the universe moved in the gentle grip of gravity, that this was the system of the universe. And yet here was evidence that somehow a magnetic force could also reach across space. The question was, how do you prove it? Well, on the 1st of September 1859, Richard Carrington, an amateur astronomer, was in the right place at the right time. This is his observatory and house at Red Hill, and he decided to take up the baton from Schwaber, and he would take on the work. He would make the biggest, the most accurate, and the most detailed catalogue of the sunspots that had ever been taken. And so it was that this day, just after noon, he had finished his sketches, and he was starting to time the movements of the sunspots. Now, this is one of Carrington's sketches. This is of the sunspot that day. I've put it in conjunction with one of the Halloween sunspots as well. Carrington's sunspot is, it's around about 10 times the diameter of the Earth. And as he was timing the movement of the spot, so two brilliant beads of light suddenly appeared on the image. What he was doing, he was projecting the sun through his telescope and down onto a board. And on this board, where he saw a full image of the sun, so appeared two brilliant kidney bean shapes of light. Now, what he's marked here is point A and point B. Now, they were so searingly bright that he instantly realized he was seeing something that no one else had ever described, that this was something totally new, totally unique. He writes that he was rather flurried by the surprise of it all. That didn't, however, stop his scientific instinct kicking in and him in taking down the precise time at which this happened. He then ran out of the observatory into his house looking for a servant, and he tried to find somebody to come back and witness what he had seen. Well, he doesn't actually say whether he succeeded in finding anybody to come and witness, but he does say he returned no more than 30 seconds later and was most disappointed to see that the lights had already significantly diminished. Well, he tracked them for the next several minutes, and they moved across the sunspot group and finally disappeared as two tiny points of light at C and D, as he's marked on there. And don't forget that the distance that they've moved in a few minutes, that's several times the diameter of the Earth. When he was doing the calculations later that evening, he realized that these things had been moving at colossal speeds that were just frankly unbelievable. And so he then went on a concerted effort to see if somebody else, another astronomer, had witnessed the same event. He simply knew he would have a hard job persuading anybody if he couldn't find an independent witness. He went first to the Kew Observatory in Richmond, built by George III, and here one of Carrington's colleagues was engaged in the daily photography of the solar surface. It was an experimental device, and when Carrington got there that day, he asked if anything had been seen, and unfortunately no picture had been taken that day. But the director of the Kew Observatory said, "We do have something strange to show you." He took him down into the basement of Kew, into a pitch-black room. And in this pitch-black room was hung a magnet on a silken thread, and pasted to the front of the magnet was a mirror. This was suspended in the room, and a beam of light was shone onto the magnet. This beam of light bounced from the magnet and hit a rotating drum. And the drum clockwork device had a piece of photographic film placed around it and would gradually turn every day. Any changes in the magnetic field of the Earth would cause the compass to wobble, that would make the light deflect, and so it would trace a path on this photographic film. And when they unrolled the film to show him from the day before, there, at exactly the time that Carrington saw the flare, was a spike. It was as if the sun had reached out and struck the Earth and set the magnetic field ringing like a bell. As Carrington stood in the observatory, so the magnetic field of the Earth was still jittering. And in fact, it wasn't diminishing, but it was getting stronger and stronger and stronger, far exceeding the spike that coincided with his flare that he had seen. This was the night of the giant aurora. Unwittingly, Carrington had been in the right place at the right time to see the flare that precipitated this giant eruption of material that would then engulf the Earth and produce the largest magnetic storm and aurora the Earth had ever seen. He presented his case at the Royal Astronomical Society, and a vigorous debate erupted about this. What was at stake here was the belief that they had an almost complete knowledge of the way the universe worked. If it wasn't just gravity at work, it was magnetism as well, then in a sense, they had to go back to the drawing board. There was much more still to learn. There was no full theory of what magnetism was at this stage. And so there were a number of people that simply couldn't really believe what Carrington was saying. One of these people was George Airy, the Astronomer Royal. And he was fully convinced that there could be no way for magnetism to leap out across space. And he was vigorous and pointed in his rejection of this as an idea. And as you might imagine, the Astronomer Royal carried great weight at that time, as still does. Now, a clue was missed the year after. And this is picture, to set the scene, you can see the Victorians in their ubiquitous frock coats. This is in the middle of Spain in August. But they're still there in their hats and their jackets. And this is in River Bolosa, and there was an eclipse, a total solar eclipse that would pass across the Spanish land. And eclipses were phenomenally valuable because in those few moments where the moon sits in front of the sun, so you see the solar atmosphere. The views that I showed you before, taken with SOHO, and which we constantly now monitor what's going on. It's hard to believe that years would pass and you would just get a few minutes to see what was going on. The gentleman with his back to us in this photo is Warren de la Rue. He's another amateur astronomer. He was the man responsible for the solar photography at the Kew Observatory. And the solar camera that he financed is sitting on the tripod in the middle. Now, the structure around it is like a makeshift observatory. It's fashioned of wood. The front has been taken off so that the photo can be taken. And you can just see on the right like a dark doorway. That actually leads into the dark room. They had to construct a dark room so that they could develop the photographs that they were going to attempt to take. This was the first time anyone had ever attempted to take a picture of the fully eclipsed sun. They had no idea whether they could do it. In fact, they thought they would probably fail. Warren de la Rue reasoned that the full moon was probably about the same brightness as the solar atmosphere, and so made test shots with his camera to see if it would work. And he registered not a single thing on the photographic plate. He still went and took the chance. Now, when the front was on this observatory, and they then put tarpaulin over it so that they could constantly throw buckets of water over it because it's so hot that the photographic film simply fogged if they didn't keep everything cool. And then they had to develop it, they had to prime it, expose it, and develop it rapidly. I'm very pleased to say, here's the picture. It sits today in the library of the Royal Astronomical Society. And this is the first image ever taken of the solar atmosphere. And the feature to look at is the one that's up at sort of 10 o'clock. You can see two arches there. That's actually a solar flare launching a big eruption of gas into space, like we saw on the SOHO images. The track of the eclipse passed from this east coast of America, across the Atlantic, across Spain, across the Mediterranean, and down into Africa. And when you compare the descriptions of the solar atmosphere from observers at all these locations, so you see on the eastern seaboard of the States, an observer saw a bright flash that he couldn't be certain was real or not. Suddenly, boom, that was the flare gone. And then as it comes across Spain, people saw this bubble opening up to become a tulip shape and moving off into space. The trouble is, nobody knew really what they should be looking for in the solar atmosphere. They didn't know if they could believe these stories of what was seen. And the fact that different observers saw different things, they weren't sure they were all seeing the same thing. The photograph was a double-edged sword in a way, because it said, here's a photograph, here is something, in black and white, literally, that we can all agree on. But of course it didn't take into account the fact that this structure changed and moved. And so they didn't recognize the true dynamism of the solar atmosphere and didn't link this up with a similar event to the bright light that Carrington saw. Our story takes a little bit of a leap here because Carrington never lived long enough to pursue this research. And what seemed to do for Carrington, in fact, was that he was a gentleman of leisure, had a very healthy living from his an income from his father's brewery in Brentford. But his father died prematurely, and Carrington had to take over the family business. Working for a living seemed to come as quite a shock to the system for Carrington. But I do have some sympathy for him. He had begun an unbelievably punishing regime of scientific research. his catalogue of, first he catalogued stars, he then also started cataloguing the sunspots, as we talked about. And it wasn't just a case of making sketches and doing a few timings. He then had to reduce all his measurements into hard numbers that everybody could agree on, because he realised that he was seeing the sunspots as seen on a globe, and he was projecting those onto a flat surface, so he had to make corrections and what have you. And he had to do all of this work by hand. So for every day that he observed, he had days' worth of mathematics to then do. Essentially what happened to Carrington is trying to run the family brewery and trying to keep up his scientific research resulted in him having a nervous breakdown. And he abandoned everything. He left, he sold the brewery, he sold his observatory, and he tried to retire. He then made the most disastrous marriage you can possibly imagine. I'd always wondered why Carrington sort of seems to just disappear from history. You read about this amazing astronomer whose his proposal to the Royal Society reads like a who's who of Victorian astronomy. He was in the top echelons of science, and yet you hardly ever hear about him today. Well, a little bit of digging, and you find that this marriage resulted, I'm not kidding, in scandal beyond belief. In fact, I joked at the very beginning of wanting to write this book. I said, I know what the title is. It's Sex, Drugs and Solar Flares. Obviously, I won't air Carrington's troubles in public, but in the spirit of fair and complete journalism, I researched it and put it all in the book. Interestingly enough, in the year that Carrington dies under suspicious circumstances, Walter Maunder was just taking a job at the Greenwich Observatory. Walter Maunder was one of the first to be employed in an open and fair system based on ability and not the old boy network. And this drove George Airy absolutely mad. The Astronomer Royal couldn't stand Walter Maunder and seems to have terrified him. Maunder was carrying 2 vials of photographic developing fluid one day through the observatory, caught one sight of Airy stalking towards him, and dropped the lot. Just the thing you want to do when you're trying to impress a boss who's already not convinced about you. That very day, probably a few minutes after, I suspect, Airy dashed off a letter to his superiors saying, Walter Maunder is the veriest dummy I've ever come across. He said the wrong man was chosen for this job. Anyway, Maunder managed to survive. He kept his head down, he persevered, and what he did was to take over Carrington's work and the work of Warren de la Rue at Kew, and he took daily photographs of the sun, he monitored the sunspots, and he also kept a lookout for when there were magnetic storms on the compasses at Greenwich too. And together with his wife at an eclipse in the 1890s, he took this image, or she took this image, Annie Maunder took this image of the sun. This time you can see the most amazing streamers in the atmosphere. The problems of trying to prove that sunspots could somehow give up magnetism that would hit the Earth was made much worse when Maxwell developed his theory of electromagnetism, and the concept of the force field was born into physics for the first time. And this imagined that if the sun was a magnet, then somehow it was surrounded by magnetism. And the biggest cataclysm you could imagine that could happen is for it to reverse polarity, up and down. if you were to do that, if you do the calculations of how much energy, magnetic energy, that would release and radiate all through space, it wasn't anything like the quantity of magnetic influence that you were seeing on the magnetic storms. Thus went the reasoning from all the people that believed in the mathematics of Maxwell wholly. It proved that magnetic storms couldn't come from the sun. But after 30 years, Maunder knew that when you had sunspots, you were likely to get magnetic storms. And when you looked at the data of when you had magnetic storms and there appeared not to be any sunspots, if you just tracked back, the last time the sun rotated round in your direction, there had been a sunspot there. So he was starting to think that sunspots were just a sort of visual manifestation of an overall magnetic blemish that grew and then produced a sunspot, and as the sunspot died away, so the magnetism followed it at a later time and died away. And he said, with this picture, look at these big beams. What if magnetism could somehow be projected like a searchlight beam? Or a big magnetic cannonball could be somehow thrown off the sun and strike the earth. Then you would be able to have enough energy because you wouldn't be radiating it wastefully all the way across the universe. Now remember, this is like saying you just don't believe in gravity or something like that. He simply said, I know there's a theory, and I know it seems to work for a lot of applications, but I think there's more to find. I think this is a signpost that there is new physics that we don't understand. And indeed, soon in the 20th century, they discovered the quantum theory and the idea of particles carrying electricity and magnetism, and essentially proved Maunder's idea about the magnetic cannonballs. Now, doubtlessly, I'm going to get asked that question. So, the Victorians were principally interested in whether the sun could affect the temperature and the climate of the Earth, the sunspots, I should say, because there was some reason to believe that the number of sunspots also seemed to coincide with good and bad years of harvests and things like that. That's one of the reasons they began to look into the sun. The modern view is that the sun is not responsible for global warming, that man-made emissions are the driving force. If you look back, however, at the records, man-made emissions probably only rose to dominate the solar influence, the magnetic influence of the sun on the Earth's climate within the last few decades. So up until around between 1970 and 1980 or so, the surface temperature of the Earth and the climate could very well have been driven by magnetic activity on the sun. And this raises an extremely interesting point. How much now is due to man-made emissions, and how much is due to the sun? Well, according to a number of lines of research, it would suggest that perhaps up to about a third of modern warming is caused by the sun still. We know that the sun is in a very unusually active time, magnetically active time. And although the pathways are not fully understood about how this magnetism can affect the surface temperature of the Earth, there seems to be some evidence for it. The worry here, the worry that I have in all of this, is that if we steadfastly refuse to believe that the sun has even a small influence on global warming, if the magnetic activity of the sun were to lapse, then it's possible that what we perceive as global warming could change. It may even go down slightly. And if we're not willing to believe that there could be a natural force involved here as well, then we play into the hands of the people that say, you don't understand global warming, we don't need pollution controls, we don't need to worry. Go away and understand global warming more before you bash us over the head with green taxes. So, on that depressing note, I shall leave you there. I'm quite happy to answer any questions that you have. More than happy to talk with you over a glass of wine afterwards, so long as I'm first in the queue. I think Jeff is the keeper of the microphone, so he gets to decide who asks the questions.
You mentioned Walter Maunder.
Yes.
Is it just a coincidence, or is there a family connection with Michael Maunder, a currently famous photographer of solar eclipses?
Yes, I know him actually, and I've never asked him the question. So I've no idea. Perhaps I'll email him tomorrow.
As the burning of the hydrogen to helium is progressing outwards to the surface, doesn't it mean that we would expect that the sun's output to in fact increase and cause global warming?
The sun's output will increase with time. It has increased with time because, as you say, of the changes in the chemical composition of the core. However, that takes place on a timescale vastly larger than we're talking about with global warming.
I just wonder if we could go back to the communications problems that you mentioned with the Halloween eruptions, and whether you could give us some idea of presumably they were measured in terms of, microvolt per meter or picovolts or whatever the electrical interference was. And secondly, was it across the whole frequency spectrum? Are all communication systems vulnerable then, from a few megahertz up to the gigahertz?
Technical question. Want numbers and everything. Essentially, the true answer is that I don't have the figures in my head. As I understand it, a vast swathe of communication systems are affected, perhaps differently for the different characteristics of different storms, even to the extent I saw some research suggesting that mobile phones and things like that, they can also be disrupted because of the effects of these solar storms. So if the question is, can we switch to safe frequencies that we know won't be affected by these solar storms? I think the answer is no.
Yes, I've got two points, questions, if you like. The first one concerns the Southern Cross and possibly other ships at sea. Did they report any wild swinging of the compasses? The second thing I have to make a remark on is Maunder. He, of course, was the discoverer of the Maunder minimum. I don't know whether you'd like to say a few words about that coinciding with the extreme winters in the Northern Hemisphere.
Yes, certainly. Your first question about the compasses, yes. I mean, all the compasses on the Earth went haywire as the solar storm hit the Earth that night. And then Maunder as well as taking his own decades-long catalogue of sunspots, he also then began to look back to historical records through people like Carrington, through people like Schwaber, and back centuries before to see who had catalogued sunspots and who had noticed sunspots. And he saw an amazing thing. And that was that between the years of 1645 and 1715, there appeared to be virtually no sunspots visible on the sun. This is the period of time called the Maunder minimum. it is also the period of time that coincides with the worst years of the so-called Little Ice Age, and is another piece of circumstantial evidence that somehow the sun is magnetically linked to the Earth's temperature. And this is, I was going to say, this was what I was alluding to really when I said if the magnetic activity of the sun should change drastically now, we could lapse into another Maunder minimum, for example, and that would seem to depress the solar influence on climate, whatever that is.
Coming back onto your earlier reference to the electromagnetic storms which are coming from the sun, and the reference that it affects communications and so on, and particularly also the mobile phones. There have been always these investigations in how dangerous the electromagnetic thing is to the human brain. And with the enormous amount of power and electromagnetic power and electromagnetic radiation which comes from the sun, we seem to have been, through hundreds and thousands of millions of years of evolution, been subject to this radiation anyway. So is there actually a correlational investigation going on where you said, well, never mind the small amounts of electromagnetic radiation on mobile phones, what about the electromagnetic radiation we are subjected to those storms, not on our communication systems, but on our brain?
We are beautifully shielded from all of this chaos by the atmosphere of the Earth and by the magnetic field of the Earth. So these amazing, this amazing space weather that goes on doesn't actually reach the surface of the planet in any sort of dangerous form to us. It will do if you're on Mars. You'll get the full force of it. And where it affects communications, that's because it's disrupting either satellites or it's disrupting the ionosphere, which is causing all sorts of electromagnetic effects which can interfere with telecommunications signals. It's really the fear that it might be a problem that caused those aeroplanes to be diverted. And I should say as well that scientists are divided at the moment about whether a high-flying aircraft is actually at any danger or not.
Just following up this, I mean, your example of the telegraph, where people were injured by violent sparks, I mean, that rather goes against what you've just been saying, doesn't it?
Well, if you have, you can still have extremely large electrical currents travel through power cables and things like that. It's just these days we don't tend to connect people to the other end of these long wires. However, in 1989, transformers in a Canadian power station were completely melted by a solar storm, and that blacked out millions of people in America. And there have been other power supply problems and power station problems. Pipelines, oil pipelines, they have tremendous currents surge along them as well. So precautions are taken to try and deal with that and not have any injuries caused because of it.
I was wondering, is it true that solar storms can have either a positive or a negative polarity, and that if that is the case, the one is worse than the other? And if that's true, why is that?
Yes, the sun and the sunspots themselves do appear to reverse polarity every 11 years, and if the Earth's magnetic field doesn't. And so there are times when you can get solar storms with sort of the wrong polarity, if you like, and it makes Earth a bit more shielded from them. Other times when you get the polarities being exactly right, they can help feed in to the Earth. They can be more damaging storms. The way I think of it is like if you try and put two like poles of a magnet together, they repel. If you turn them around, reverse the polarity of one and put them together, then they'll attract. And so, yes, I understand that the conditions in 1859 were absolutely spot on for a perfect solar storm, so to speak.
We have one rule that we start at 6 and end at 7, and it is 7 now. Thank you all very much for coming. Do buy the book, it's wonderful, I promise you. Our next lecture is on Monday, and it's about conquest and disease. We sort of like disasters at Gresham. And indeed, the following night there's a lecture on the American presidency. But now, thank you for coming, and Dr. Clark, thank you very much for a super lecture.
You're welcome. Yeah, thank you.